So, welcome everyone to this first edition of the Software Developer Thursday 2022. First of all, Happy New Year to everyone of you and everyone who is looking online this event. I'm really happy to have here Riccardo Scilla of Eurac Research that will present us a TensorFlow-based algorithm for sensors. So I won't steal more time to him and I will pass the microphone to him. So thank you.
Thank you. Good evening, everybody. I'm Riccardo, and I'm a master degree student at the University of Trento and a trainee at the Eurac Research in the Center for Sensing Solutions. Today I want to talk about the TensorFlow algorithm for the calibration of low-cost, high-quality sensor deployed in a station here in Bolzano. This is a part of a bigger project called FIRST, which stands for Artificial Intelligence for Wireless Sensor Networks. Let's see what I will talk about today. First, I will introduce you a little bit of the setup of the sensor together with the data workflow that we have to process the data. Next step is to preprocess the data that we acquire from the sensor, and then we can try to calibrate implementing some model in TensorFlow, but also some simpler calibration models in Scikit-learn, such as the support vector regression. We have an important distinction between the dataset, between the train and test set that we use when we want to calibrate sensors. In particular, we have shuffle, train and test set, and non-shuffle, train test set, and I will show you what I mean by shuffle and non-shuffle. First, let's start with the setup of the sensors. The sensors are, the local sensors are placed in an upper station deployed in Bolzano, and here we see that the station, in the station there are two tubes that brings the air from the outside, and this allows us to have a constant flux of air, from which we can measure the pollutants and some other atmospherical features using the sensors. In the first tube, we have the reference sensor provided by APA, while in the second one we have the local sensor provided by us. Once the data are collected, we can push them in collect them into some influx databases. We have two, one for the APA data and one from the first. The APA data is provided by the Open Data Hub and contains many pollutants, such as the NO2, the PM, and also some other atmospherical features like the temperature and relative humidity. While our data, the local sensor data, we have NO2, O3, and also some other pollutants, some other atmospherical features like the relative humidity and temperature. So, speaking about the data workflow, we have that the data provided by APA is obtained via API through the Open Data Hub, and we already said that we push the data to the influx databases. Now we can obtain them and visualize them using a Grafana dashboard that is implemented, and this allows us to see how the data goes over time, and we can also see if there are problems, if the sensors falls down. So can we intervene to bring them up and continue use these sensors. For what concerns the the computation, we use the Jupyter notebooks, for which we can use the computational power of the Center for Sensing Solutions. And then, because this project involves also some other people, like a student from the University of Bolzano and me from the University of Trento, we have a GitLab folder where we can share all the code that we build, all the features of this project. Now let's start with the data pre-processing steps. So we already said that the data is pushed to the two databases, the alpha one, the two influx databases, the alpha and first. This data now need to pass some pre-processing step in order to be used from the TensorFlow algorithm. First we need to clear the saturated values, because when the sensor goes down we have 0 values or 100 values saturated that need to be cleared. Then we resample them at 1 hour so that we have all the data at the same time, and rescale also the units so that they are comparable. At the end, we can join these two databases together to obtain a bigger pandas data frame, for which we can start building our models. First, let's see at the O3 that will be used also in the later experiments. We can see the O3 data row. And clearly there are two major problems. One is the presence of outliers, so some points that falls really outside of the trend of the time series, and this one need to be removed because can slow down the quality, lower the quality of the calibration. To do this, we used the Prophet, which is a tool from Facebook that allows us to decompose the time series into 3 components, one for the trend and the other for the seasonality, like daily seasonality or weekly seasonality, and some error. By combining back all these components together, we obtain the picture below, where we have the time series and a band, a confidence interval around it that stand for that represent the 99% confidence interval. All the points that fall outside this confidence interval is marked as an outlier, and so we can remove them. The second problem is the presence of gaps when the nodes fall down. And to solve this, we do not simply cannot simply cut the time series and merge them together, because this will break the seasonality that we found in the Prophet. So to remove the gaps, we need to find particularly hours where the seasonality can be merged together to have a continuous time series over time. At the end, we obtain something like this. With in orange we have the reference of 3 measurements, while in blue we have the pre-processed one. And as we can clearly see, there is a huge gap between them, and this is what we want to remove using the calibration algorithm. First, as you know, to implement a machine learning algorithm, we need to split the dataset into train and test set. The data is split considering the 20% of the data for the test, and there is another parameter, in this case that is the shuffling or non-shuffling. In the first case, we can take shuffle the data, so taking the 20% of the data by sample them evenly in the time series, or without shuffling, we take the last 20% of the data for the test and the initial 80% of the data for the training. These are 2 different approaches. The first one is commonly used in machine learning, so because this allows us to have more balanced statistics in the train and data set, while the second one is more suitable for what we want to do in the first project. That is, we want to calibrate the sensor using an initial period and then see how much the calibration we found is reliable over time. First, we will investigate the shuffle train and test set to evaluate the quality of the model, and then we will see also what are the performance of the model that we trained, also in the second case of the non-shuffle train and test set. The first model I want to talk about is the support vector regressor. This is a classical machine learning model, and without going into much detail of the math, the idea is to find the hyperplane that maximizes a margin. And this margin is defined by the two epsilon, which is called the epsilon tube. Every point that falls outside this epsilon tube defines an error that we want to minimize. This is linear regression, but usually we don't have linear regression for calibrating the sensor. So for non-linearity, there is a trick to do that, that is to map our points into a higher dimensional space defined by the phi of x, where probably hopefully the data are linearly separable. And then we can map back using the inverse of this function to the initial data and have the regression function in the non-linear case. The support vector regression model is implemented easily using Scikit-learn. We have different parameters like the kernel, in this case there is the radial basis function. Then we have the cost and the gamma, that are parameters that I explained before. That is the cost of having points outside the tube and the size of this tube. To find the best parameters, here we can use a technique called halving grid search cross-validation. In this technique, we define first the model, so the support vector regressor, and then we take this model with the parameters, and we try to find all the best combination of the parameters that maximize the results using our train and test set. Using our train input with the train output. The best model is then trained with the parameters found using the cross-validation, and we can then predict starting from the test set and compute some loss functions using the output of that we have in the test set. Looking at the results using this method, we can see that the loss function used here are the R2. It is a function that goes, a matrix that goes from 0 to 1, so can be seen as a percentage, and we achieve a 0.92%. And then we also have some other metrics that are commonly used in regression problems, such as the root mean square error and mean absolute error. By looking at the results of the plot of our prediction, we have that now the two time series are pretty much aligned if we compare with the initial situation that we have, where there was this huge gap. Now the gap is reduced, and the two time series follow the same trends, the same peaks, and also where there are small value, near zero value, the time series are pretty much aligned. Let's now start talking about a little bit of the TensorFlow models. The first model I want to talk to you is the multi-layer perceptron, which is the simplest network that we can build, starting from the structure of a single neuron, that is the perceptron. And this is composed by different layers because of the multi-layer. We have an input layer where we can input our feature measurements. Then we have a sequence of hidden layers followed by activation, non-linear activation function that help us learning non-linear dependencies. And at the end we have a single neuron as output, because this is a regression problem where we want to find a value that is in a real value output. As input feature, we can have different features. We can start by taking as input the O3 of the local sensor only, but then we can also use some atmospherical features like the temperature and the relative humidity, but also some other pollutants like the NO2, which we know that has a strong cross-sensitivity with O3. At the end, we can output, the output of our model is the O3 calibrated, that is compared with the reference to compute a cost. And this cost is then used to update all the weights, which means all the connection between every neurons, to improve the performance and train, educate our model. Before putting our data into the model, we need to do some data preparation. One important step in neural networks is to normalize the data, and this is done using the min-max scaler. So we can define the min-max scaler that allows us to put the values in the range 0, 1. We can fit and transform the feature data, and then transform also the feature data for the test set. This is more or less what we obtain. So in the first matrix, we have that all the numbers are in the ranges that we read from the local sensors. And then after this normalization step, we have the values in 0, 1. The next step is to prepare the data to be suitable as input of the multi-layer perceptron. And this is done using a reshape function, basically reshaping the data in a way that we have a sequence of arrays, and every array contains all the features that we want to input in our model. If we print at the end of this step the shape of the train and test data, we will have that we have more or less 1,500 samples with a length 4, because we have 4 features here. And this is the case also for the test set. In this case, we have the 20% of the data. While for the Y sets, we have only one dimension, because the only value that we have is the reference value. Now we can build a model using TensorFlow. This is done for first defining a sequential structure that contains all the layers that we want to input in our model, that we want to use to build our model. First, there is the input layer that contains the 4 shapes, the input shape 1, so the second dimension, the 4 features. And then we can start adding to the model more layers fully connected that are called dense layers of, in this case, 32 neurons with the nonlinear activation function, in this case, the ReLU. At the end, we want as output just one single neuron, so the output will be dense with just one neuron 1. Once we have built our model, we need to compile it. And this is done defining first a loss, in this case the mean squared error, which is a common loss for regression tasks. Then we need to define an optimizer, in this case is Arden, with a learning rate of 0.01. This function returns our model that now is ready to be fit using the data. In the fit function, we input the train scaled and the Y train. We define also the number of loss, the number of epochs, in this case 1000. Then we can define also if we want to shuffle our data inside the train set, and this helps the training. Also some other parameters like the batch size, that is the number of data points that are put together inside at each iteration of the training. And we can also define a validation split. So once we have our trained data, we can select, for example, 10% of this data to be used for the training itself. And this is used, for example, defining a callback, like the early stopping callback, to verify how our training is going on during the epochs. With the early stopping callback, what we want to do is to monitor the loss of the validation set and stop the training if the validation loss does not increase for more than 50 epochs. And this helps us to not overfit our model and to stop once the model is ready and found the best set of weights. We can also print our model structure with a summary function and see what all the layers that we put together with also the number of the trainable parameters. Some results. Let's see first with a single feature. In this case, only the O3 of the local sensors. We can see the effect in the first plot. The effect of the in the first plot we plot the loss of the train and the validation set. In the loss of the validation set usually decreases over the epochs, while the validation set might also increase depending on how the train is going on. And we see that the epochs stopped really earlier, because for 50 epochs it doesn't find any improvement in the validation loss. The result of this calibration is of 0.66 as R2 score, and we can see also in the second plot the predicted value, the time series in the plot in orange, is aligned with respect to the initial point, the starting point of the raw data. But also the peaks, some peaks are not messed, and also the value near zero sometimes are not aligned. Working with multiple features, we have an increase of the R2 score, so we achieve 0.74, and the time series predicted is now more aligned with the one of the reference. Up to now, what we have done is to consider just the single value that we have for the local sensor to predict the reference value. One thing that we could do is to consider the time into the model, and this is done by taking a window around our data. We can, for example, choose to include as an input not only the value of the local sensor in the current timestamp, but also take into account the values of the previous and the next timestamp to predict the one of the current reference. This is done using a function which takes as input all our data and the number of steps that we want to include before and after. This will increase, of course, the number of input features from 4 of the previous case to 12 of, in this case, after this step. Using all these features now to predict our calibrated time series, you can see that the value now is, the R2 score is increased with respect to before, that was 0.74, now it's 0.90, and we achieved again good results with respect to the beginning, the raw data. Now we will see some other techniques, some other models that we can use to calibrate our sensors. For example, the long short-term memory, which is a recurrent neural network. This model is typically used when we have data that has temporal dependency, like for example text, videos, or voice, or also time series, like in this case. It is made of, again, an input layer, where in this case we can input the features at different time steps. But in this case, if we look at the scheme, the first neuron in the LSTM layer takes as input only the values of the current time step, at the time step t. When we go to the next step, the t+1, we input the features of the current time step, so the t+1, and also the information coming from the previous step. And this is done through to the end of the network to take into account all the possible dependency over time. At the end, we can output a single neuron, as an output a single neuron, but also we can modify the network to output all the hidden states of the different cells. From this point, we can append other neurons, for example, dense layer as we did before, and obtain, in the last part, a Monterey Perceptron that outputs a single neuron as before. To do this, we need again to reshape our data to be suitable as input of the long short-term memory. And in this case, the reshape is done by taking into account the time. So we will have, for example, the 3 time steps as input, and in every time step we want all the 4 features. By looking at the shape of the reshaped data, we will see that the number of samples is always the same for both in train and test set. But now we have 2 more dimensions, one that refers to the temporal information, and the other one for the feature. So 3 is the number of time steps used, and 4 is the number of features used. Now we can build our model, which is similar as before. We define first our sequential structure. We input the layer, in this case, with 2 dimensions, one for the time and one for the number of features. We can then put our long short-term memory network, in this case with return sequence true, which means that the output of the hidden state is used, and this should be followed by a flattened layer that flat all the outputs of the previous of the LSTM output. And from this point we can append the dense layers as we did before, and the output with the dense one. As before, we build the model, we compile it using the optimizer and the loss, and we can then fit our model using the training data, as we did before, and print also the structure of the network that we have in our model. By looking at the results, so now we see that the R2 score is increased with respect to before. We achieved like the support vector regressor, the 0.92, and the time series is aligned as it's better aligned with respect to the previous model that we built. The last model that I want to show you is the convolutional neural network and how to use convolution for time series. The convolutional neural network is used especially when we have to work with images, because it is capable to extracting neighborhood dependencies information around the center of our convolution operation. So we can define our matrix in this way, putting the features in time steps. We have, in this case, number of rows is the number of time steps used, and the number of columns is the number of features. We define a window, in this case a 3x3, where we can apply a convolution operation, and this outputs as an output a single value for every convolution around this matrix. And at the end we can again put another dense layers and a final output. We need to reshape in this case also the data, where as I said before, we have the number of rows is the number of time steps used, while the number of the features, the columns, is the number of features. And if we print the reshaped data, we have that we need a fourth dimension, because the convolution needs that every value is inside a single array. But we can see that the number of samples is the same. The number of the second dimension is the time, and the third dimension is the number of features. We can build the model starting from the sequential and an input layer. Then we can apply the convolutional 2 dimension with defining a number of filters used in the convolution, and the window size, in this case, a 3x3. The padding same is used to have as output the same dimension as we have for the input. Then we plot the output of the convolution, and we apply more dense layer with a final dense layer for the regression task. Again, we can compile it with the optimizer and the loss, and also fit using the train X and Y, and see the structure of the convolutional layer with the outputs and the number of trainable parameters. As a result, we achieve with this network 0.91, which is more or less in between the Monterey Perceptron and long short-term memory. And also visually, this improved the results starting from the raw low-cost sensor data. Now, by looking at all the models that we built so far using this shuffling of the data, we have that the models, the neural network models built with TensorFlow, all achieve good results over the 90. but still the best one seems to be the support vector regressor. In this case, because even though it achieves the same R2 score, there's a lower value of RMSE and also quite smaller value of MIE. Let's see now the second case, that is the one without shuffling the train and the test set. So in this case, we use the first 80% of the data for the training and the last 20% for the test. This we can apply different models, but in this case we compare the two most important models that we found before, so the support vector regressor and the long short-term memory. With the support vector regressor, we see that, that starting from the raw data, the one in green, we are able to put down to close the two time series, so calibrate them. But we have problems near zero because the one from the reference are pretty much flat, while our are oscillating a bit, and the R2 score at the end is 0.60. So quite lower with respect to the case with the shuffling data. By looking at the long short-term memory model, we achieved a better result with respect to the support vector regressor, 0.76, which is again lower than the 0.90 that we achieved before, but is better than support vector regressor. And now the values near zero are pretty much flat, and this also helps the loss function to have a better result. So what we have seen a little bit of the setup of this where our data is captured, the pre-processing step to apply to clean the time series and have more quality data on the measurements done by the sensors. Then we have seen the two cases of using the training test shuffled or non-shuffled, with the comparison of different models, classical models like the support vector regressor and neural networks with TensorFlow. Some take-home message from this work is that the neural networks seem to outperform the classical machine learning models in the case of non-shuffling settings, while it has comparable results with the shuffle the shuffle settings. We have some issues when we want to use neural networks. The first one is the repeatability of the results, because the weights are set randomly every time we build our model. So another point that we can investigate is how to optimize also the stability, and this is commonly done by using more data to have a more stable training. Then also the neural networks require a more important parameterization, because different parameters can be set to achieve better results. For example, we can start from the pre-processing parameters, such as the resample frequency. We resample at 1 hour, but we can also try with 30 minutes or 2 or 3 hours. We can also play with the temporal window size. So without using the -1 + 1, we can use -2 + 2, and so on, to see if we can achieve better results. And also, of course, we can also tune the parameters of the model, and this is commonly done using a trial and error process. So changing manually the number of layers, for example, or the number of neurons in each layers, and see if we can fine-tune the model. In cases of simpler models, the number of layers and the number of neurons should be smaller because we don't need too much computation to get our results. So as principle, we work with lower number of both layers and neurons per layer. And then we can also play with the model parameters like the learning rate, optimizer, or batch size used. So thank you for your attention. And if you have any comments or questions, also suggestions to something else to try, thank you.
Sorry, I was a little bit late, maybe it was said, but did you also try some classical statistical tools like linear regression?
Yes, we tried also simpler models like linear regression, multiple linear regression. Linear regression, we also used, we tried also some classical calibration, semi-classical calibration by taking into account specific conditions, for example, same condition of temperature and relative humidity, and see if we can find a linear function that fits our data. But the results was really lower than the ones that we see today.
I've got one question. So, first of all, thank you for your presentation. My question is the following. So, I suppose at the end of each model you explained, you get a function, transfer function, which depends on the raw signal and all the trainable parameters. Is that right?
Yes, at the end,
okay.
Yes.
Yes, at the end. The question is, how many parameters did you use in this model? Which is a couple parameters or tensor?
The parameters are the low-cost sensor measurements of the one that we want to, of the reference one. Yes. So in this case, the ozone of the low cost. And we then applied a feature extraction to using the data to see the ones that are that were more correlated with the reference one. And it comes up that the temperature and relative humidity were good features, and also the NO2.
Okay.
So we put these four together to achieve these results. And as we see, we have seen using one single feature, so with respect to all the four, the results were really different.
Mm-hmm. Okay. And which one is the most important?
And the most important, of course, is the raw.
Oh, well, a part of the raw signal, okay.
The relative humidity.
Okay.
If I remember correct.
Anyone else has some comment, question? Otherwise, I do have one. Did you make some comparison also from a performance and requirements point of view?
For example, the time to compute them?
Time to compute, need for memory resources and for CPU resources.
The new for the neural network models, neural network models, I use the GPU for improving the result, the performance speed. For example, the LSTM took around 2 minutes to train with CPU, while 20 seconds with GPU. And the support vector regressor was quite good, was in speed. Memory, I didn't examine it.
Some other feedback, question? Do we want to make a short presentation round of every one of us, just saying name, surname, and a short description? Like, I'm Stefano Seppi, I work at the digital unit of Neutech Park, and I am one of the organizers of this event. So thank you for coming, and I pass the word to you, but everyone of us know you, so maybe can you go on?
Okay, my name is Christopher Nuster. I'm establishing an incubator in Switzerland, just across the border in the Netz. So it's just across the border, really. It's about 1.5 hours. And we work on a couple of projects, including space-related solutions, but also some machine learning things. We're currently looking into establishing software that would recognize merchandise without referring to the barcode, so by visuals. Yeah, and that's the reason why I got somehow interested in what you do.
Okay. Thank you.
My name is Hai. Was that does not know me, I'm Roberto Monsoro, and coordinated the Center for Sensing Solutions. Thank you, Riccardo, for your really great presentation and the great job done until now. I know that you have some more steps. Actually, the comment that you gave regarding the resources is the most interesting, that I also have open question, because the final goal for us, really thanks to the this work of Riccardo, is going to be really to answer a question: are we able to place and set up, let's say, low-cost wireless sensor network, and reducing also the cost of maintenance of them? And this is really something that looks like to be feasible, but we have to find new projects how to be able to bring a good answer to this really challenging question. But really, thank you, Riccardo.
Thank you.
Gianluca Antonacci, company Cisma here at Neutech Park, environmental engineer, and I'm working on environmental data analysis and modeling.
Hi, I'm Gabriele Scarton. I'm a software developer for Group of Hosts here at Neutech Park, and I really like the presentation. Thank you.
Hi everybody, my name is Patrick Koneval. I'm responsible of the unit digital at Neutech Park, and it's great to see all this expertise coming through the team of Roberto. I think TensorFlow is very interesting topic, and also the low cost sensor network, where we also Fusion grant is running. So I think this is a very important topic for our meeting. Thank you.
Hi everyone, I'm Lisa, and I'm working here as an event manager at Lloyd, so I'm helping Stefano to organize this event.
Hi everyone, I'm Mark. I'm a PhD student from the University of Arden. Sensors technology for precision architecture.
I'm Peter. I'm one of the co-founders of Convolutional, a spin-off of the University of Bolzano. We are working closely with data and organizing data. And privately, I'm passionate about everything related to sensor data and stuff. Correct representation is very key in this question.
I'm Simon Dalvai. I'm working as a software developer and software architect here in the digital unit of the Neutech Park. And thank you for the presentation. It's really interesting.
Hi everybody, my name is Ilaria Russo, and I'm studying business informatics in Bolzano.
Okay. Thank you all for participating to this event. Thank you, Riccardo, for the nice presentation. It was really interesting. And I'm also curious to see how the project goes on, because, as Roberto said, it's a nice and interesting challenge for the IoT topic in general to reduce maintenance costs of low-cost sensor, because if I pay less at the beginning but then I have to pay a lot to maintain, it's not a good idea to go for a low cost always. I remember to all of you that we will meet here the next month is the 3rd of February. The topic will be ARM, how we'll take over our laptops and servers, the ARM technology, and the presentation will be held by Chris Meyer. You will receive from me some more information, I think, during the next week with the link for the registration and all the details of the presentation that Chris Meyer will do. So thank you for coming. Hope to see you in 1 month here at the Noise for the next event. So have a nice evening.
And enjoy the drinks.
Riccardo è quasi fatto una lezione. No, no, una bellissima lezione.
I'm also wondering why.
Perché ho specifico tema, no? Di analisi.